Well, welcome everyone. We are approaching 1 o'clock here in Arizona. Appreciate you joining and looking forward to today's session. We're going to go ahead and get started. Today's session is focused on IA-driven battery thermal management, and this is a professional development session. So today we'll cover and focus on enhancing safety, performance, and longevity with the Tesla Model 3 as a use case. My name is Brittany Holmes. I'm an associate director with ASU's Ira A. Fulton Schools of Engineering in our Global Outreach and Extended Education, or GOE office. GOE brings the vast expertise of ASU engineering faculty, enables online engineering degree programs, professional programs, as well as custom programs for industry. We also work with government and academia and support capacity building projects around the globe. Now that you know that we are, who we are, we'd like to invite you to add a little bit about yourself into the chat. So your name will appear, but please add your title, role, organization. And if there's any areas of particular interest to you in EV technologies, this would just be great for us to know as we have our faculty here joining us. So yeah, we'll give you a moment to start adding your introductions into the chat and would just love to know who's in the room with us. Today's session is part of the ASU Engineering Professional Development Series, and our goal is to connect all of you, whether you're students, faculty, or current professionals, or perhaps some of the ASU alumni, with engaging professional development opportunities. Our agenda today includes a presentation by our esteemed faculty colleague, Dr. Kanan, who's a professor of engineering at ASU's Polytechnic School. We'll have some time for Q&A, and then we'll conclude with a wrap-up and any next steps or additional opportunities. We would like to invite you to enter any of your questions into the Q&A feature. And then feel free to add your comments into the chat, but the Q&A will help us make sure that we get to any questions that you might have. And while all attendees are muted for this, we hope you'll engage with us through our polls, through the Q&A, through the chat. We would love to hear from you. With that, I'm going to go ahead and introduce our presenter today. So I'm honored to introduce Dr. Kanan, who has over 30 years of experience in fuel cell and battery research and development. His expertise spans fuel cells, PEMFC, DMFC, AFC, batteries, SLA and Li-ion, and solar cells. He joined ASU in 2005 and holds a PhD in batteries and fuel cells from the Indian Institute of Science, Bangalore. I've had the privilege of working with Dr. Kanan for a few partnerships, courses in the past, and I always appreciate the expertise he brings both to our local and our global communities. So with that, I will hand it over to Dr. Kanan to get started.
Okay. Thank you, Brittany. Good afternoon to everyone. Yeah, so I'm going to briefly talk about the AI, artificial intelligence driven battery thermal management. So I just give a simple schematic here. So in other words, the batteries used as of now may not be AI ready, but otherwise there are major companies trying to design, develop, and evaluate smarter and more AI, AGI, ASI enabled battery management systems, meaning we want the battery management system to think like humans before something happens to the battery's thermal characteristics. So when we talk about thermal characteristics, it's a real issue when you look at these pictures. So that's mainly because of the flammable solvent, which is part of the electrolyte in the present day lithium-ion batteries cells. So this technology would change into all solid state batteries, but we are not I don't think anybody can expect that to happen with all solid state batteries in the EV in the next at least 1 or 2 decades. So until then, whether we have these or maybe, more advanced batteries, we need to have a agnostically active battery management system to take care of the thermal activities or thermal issues or thermal runaway issue, because that's the most prominent catchy phrase, because if something happens in one of the cells, it's not going to stop there with the thermal event. It's going to expand. So these lines show you the ideal operating temperature for the batteries in the electric vehicle. So perfect conditions are between like a 16 to 25. That'll never happen, right? So, but most of the times, batteries would operate from, say, close to 0 degrees Celsius all the way up to 35. But if the battery temperature goes beyond sub-zero temperature or above 35 degrees Celsius, that is where the issues are going to pop up. That the reason is, all these battery systems would operate dynamically or would exposed to various operating conditions because of the drivers, because of the ambient temperature. So, in other words, the batteries have to respond to any kind of a dynamic or quicker, any kind of like a load operating conditions. And also, when the vehicle comes back to the charging station, there are chargers which also need to be more smarter in terms of controlling the charging time or charging level or voltage based on the individual cell or module or pack. So in other words, it is an issue because of this operating temperature which are exposed to the batteries. So very slow. Okay. So here you can actually see the numbers, which is kind of a capacity loss based on the temperature after about, say, 200 cycles. So 200 cycles is basically, if somebody does 5 days a week every cycle, or a charging once every day, 5 days a week, that's about, say, 200 cycles in a year. So these numbers are by comparing the battery performance at 20 degrees Celsius. So when the vehicle is being operated without any thermal control, so 25 degrees, that's a capacity loss or capacity fading of about 3%. And in other words, if you want to compare in terms of cycle life, so that's not much reduction because the temperature is not far away from the 20-degree reference temperature. However, if you go to 30 degrees Celsius or 86 degree Fahrenheit, the loss in capacity is about 4%. That's very true. So sometimes it could be even slightly higher also. That translates to almost 20% cycle life reduction if you compare that with the 20 degrees. So in the same context, if you go to 40 degrees, the loss in capacity is about 5.5. So the loss can be directly related to the range per charge in the electric car. And in terms of cycle life, that's a 40%. That's huge. But if you go to 45 degree without controlling the ambient temperature or battery package temperature, then the reduction in the capacity is about 7%, and also cycle life reduction is 50%. So this highlights the requirement for battery thermal management in a operational temperature, which is again, optimized based on the energy consumption. Because if you want to keep the battery temperature a particular temperature range, you also need to pull energy from the same battery pack, because the battery is a standalone system in the vehicle. So, I'm going to share some of the recent results from our own lab data. So this is a typical, or this is the battery module which is being manufactured in Poland by LG Energy Solutions for all the Volkswagen group of vehicles, Porsche, Audi, and all Volkswagen group of vehicles. So this battery gives you about 7 kilowatt hour. So in a typical vehicle, if you consider, typically around 80 to maybe 90, but most of the newer vehicles are with closer to 100 kilowatt hour. That 100 kilowatt hour, if you calculate based on 4 miles per kilowatt hour, 100 kilowatt hour is going to give you 400 miles range. So in other words, this kind of a module with about 7 kilowatt hour, you may put probably like, close to 15 modules in the vehicle. So this is a real battery module with multiple cells inside the aluminum cast body. And let me show you some results at different operating voltage values, right? So, most of the times when you buy a vehicle, they always say, do not go above 90% in charging. And also on the lower side, when you use the vehicle, don't go below 10% or 15%. So in other words, you have a usable range or allowable range of energy which is probably about 85% or maybe always less than 90%. In other words, if your battery is rated for 100 kilowatt hour, you are only allowed to use, most of the times it is 85%, but sometimes, once in a while you can always charge up to 90% or slightly above 90%. In other words, usable range can be about 90%. So depending on how you charge, where you limit in terms of the cutoff voltage per charge, you can also see this line. So the x-axis gives you directly the ampere hour capacity. So rated capacity is 156, but these are all done at say 25 degrees Celsius. Exactly, the module was held at isostatic temperature chamber. At different voltages, you get different capacity values. But again, it's much lower than what the company claims it as 156. So this is mainly to understand the cutoff voltage on the positive side. Everything is keeping in mind that the batteries have to operate very safely in the electric car. So with these charging voltage cutoff values, if we discharge these modules, you can actually see the capacity values different when you conduct the discharge, or this is basically when you use batteries in the electric car for driving. So the one you see with the highest capacity values, you go all the way to 3.2 volt per cell. That's about, I would say about 8 to 10% state of charge. In other words, the battery module still has about a 10% capacity before you stop it. So with that, you get almost 125 ampere hour capacity. That's pretty good. Again, these are all at room temperature. Now I'm going to show you what happens when you take this battery to lower temperature or higher temperature. So these lines you can clearly see the ones at the lowest or at the left end when you look at that at the bottom, that's at minus 10 degrees Celsius. So that capacity, it's the same current, 50 ampere current for 156 ampere hour. So it's almost like a 3 C/3 rate. In other words, if you have a vehicle, say about 70 to 80 kilowatt hour, if the range is 200 miles per charge, that means you are driving the vehicle in about 3 hours. So that's almost like, I would say that's like a C/3 rate or 3-hour rate. So at that current, okay, so this is real, right? So at that current or, C/3 rate, you only get about 113 ampere hour instead of 156 ampere hour. But at the same time, you go to 40 degrees Celsius, you get slightly higher. So maybe this is about 85% of the rated capacity. But what happens is when you use these batteries at extremely lower temperature, it is not really good for the battery. Especially when you're operating below minus 5 degrees Celsius, there can be a lithium, forming between the electrodes as a dendrite, or in other words, battery cells will start electrically shorting internally. So the internal shorting is exactly same as external shorting. High voltage cells, high power cells with larger capacity. If there's a chance for external shorting or internal shorting, it is going to be a catastrophe. That's a real thermal runaway. So we exactly know what happens in the vehicle if the vehicle is being exposed to only lower temperature without any thermal management. At the same time, at higher temperature, you get slightly higher capacity, but that is always at the cost of cycle life. You want the vehicle to operate for 100,000 miles or 8 years. That's where you get warranty for. But at the same time, these batteries made today would certainly work for more than 15 years of life with a similar operating conditions in the electric car. So now you know that the temperature has a huge difference, and also the cutoff voltages has a huge difference in terms of how much energy you can get. That energy again is equated to very clearly the range per charge. So now, especially when you have a lower temperature, so here our data has minus 10 degrees Celsius. If the battery is discharged at minus 10 degrees, it is allowed. Only charging is not okay at lower temperature, but you can still do the discharge. But at the same time, the resistance of the cells, battery cells, will be high at lower temperature, or conductivity of the electrolyte will be lower. So because of the lower conductivity or higher internal resistance, it's I square R when you pull power from the battery, or when you use the vehicles when the battery is at lower temperature. There's a huge jump in temperature. So this is an internal temperature rise when the battery is sitting at minus 10 degrees Celsius and you pull current. This is also at 50 ampere current. So in other words, at lower temperature, you have a lower power and also lower energy available. So power is limited. In other words, at extremely lower temperature, the user in the vehicle may not be able to accelerate because of the higher internal resistance. So that's again very important, that you need to manage the temperature of the battery pack in the sweet spot, which is almost about 10 degrees for at a lower temperature, because even at lower temperature, say 15, this is at the end of discharge. So maybe within say half an hour or within 1 hour, it's always going to increase the temperature by maybe 3 to 5 degrees Celsius in the pack. So again, as I said, the thermal management is very critical for the battery. So it's very critical mainly because of the performance, mainly because of the safety and longevity. So in other words, energy output in a particular cycle, safety during that particular cycle, and also cycle life. So, obviously we want to have the battery surviving for longer than the vehicle itself. So you don't want to change the high voltage battery system in between. So for that, you need to have a battery management system. So this could be a very simple, maybe, I won't say dumb, but it is not a smarter battery management system. So it could still do little bit of voltage control in terms of charging or discharging. It can also monitor current. It can also derate current if a user wants to probably accelerate beyond allowable limit. The battery current is derated so that the speed cannot be very high, or in other words, you cannot go beyond a certain pre-specified current. And you can also monitor the temperature, but again, how quickly, how accurately you monitor all those parameters and then initiate other control, that's limited based on what kind of a battery management system or BMS we have. So this is a typical, but if you want to see a little bit more improved. Okay, so this is I would say an advanced system compared to the one we just saw. It can measure the energy out, energy in, monitor the temperature both during the vehicle use or during the charging. It can also monitor, how frequently the battery was charged, whether the battery was, exposed to extremely lower state of charge or state of health. Based on those parameters, the battery can also predict the state of health and also state of charge. But, this is not really a smarter system, that it does not really worry about, how the battery's characteristics change from newer battery as the battery gets aged. Because as the battery gets aged, all these characteristics will change based on operating conditions, because the operating conditions are dynamic, because road conditions are going to change every place, ambient temperature is going to change, even the tire pressure has an influence or impact on the battery characteristics, because all kinds of vibrations and also how smooth the voltage profile is or duty cycle is, whether we drive the vehicle constantly at 25 miles or 45 miles per hour speed, always in the highway or always in the freeway. All those parameters will also influence the battery's performance, safety, and also the cycle life, because the internal battery temperature will always be, jumping to different values based on the operating conditions. So most of these, so-called advanced battery management system also have a mode called limb home mode. So in other words, if something happens to the battery, for example, this will never happen unless the battery has a manufacturing defect when the battery unit is relatively newer. But as the battery becomes older, you don't know, sometimes you sit in the wheel and then you see that the remaining miles to charge, it says like 50 miles. But then, you had only driven 2 miles and then you see that it has come down to 40. So this kind of, unpredictable or unexpected range reduction is mainly because of the battery characteristics or how the battery responds to the typical operating conditions. So these modes, because of the little smartness included in the battery management system, it'll at least, allow you to reach a safer, closest place. It will at least, help you not stranded in the middle of the road. So most of these systems, again, when the battery management system is relatively smaller, so a little bit of AI added device or with more sensors, you can also monitor the battery. So you can extend the life of the battery by following the battery cells. If you drive a Tesla, you may know that most of the vehicles have more than 5,000 plus number of cells. 5,000 number of cells are packaged in modules with like a 200 to 300 cells in a typical module, and then multiple modules are integrated in the pack, and then the pack is integrated in the as a skateboard under the seat. So you have too many things under the seat. So basically, it's a high power system, but at the same time, you have no means to control or monitor the battery by a user. So the system should be in a position to monitor the battery cells. So in order to make the battery cells, almost identical, because you have too many cells and some cells can always become weaker. That's because of manufacturing defect or maybe very slow degradation. But in none of the situations, all the thousands of cells will degrade in the same manner. One or two, the weakest link will always be there in the larger battery pack. So if you see the next slide here, so here just to show that all the cells are performing almost equally in the pack. Now, if you see here, out of these number of cells, there are 2 cells. Assume that the pack is being used in the vehicle during vehicle driving. So the weakest cells, right? So those 2 cells in this figure gets to the lowest state of charge. In other words, these 2 cells have already run out of energy. The current through the module is exactly same. So same current goes through all the cells. So now the load will still operate because the load has an operating voltage range. So with the 2 cells showing lower voltage, the module voltage may not stop the load from operation. So in other words, this is a situation which could happen in the mismatched cell or the weakest cell during the capacity discharge. But now when you charge, these quicker or weaker ones will also reach the maximum charged state quickly. So you have, most of the cells which have still room for accepting charging or accepting energy from the external power supply unit. But unfortunately, 2 cells have already reached the maximum voltage. So now the system would operate in a slightly, different way, just to deplete the cells which have much higher state of charge. In other words, the energy is actually wasted in most of the battery system because the battery management system is not smart enough or not AI controlled or AI enabled. So this wasted energy is of no use. It is a smaller bleeding resistor that it just gets heated up. These resistors are connected to the cells. So in other words, you are not using the energy for the particular purpose of driving. You are just wasting energy. So that's a passive cell balancing. There are also some systems, but not available in all the vehicles as of now. So this is again, suppose even if the passive cell balancing was not carried out, it's going to create a situation where the thermal signature is going to show up. Or in other words, those two cells are going to get heated up quickly. So in other words, within the module or within the pack, those two cells will generate a hotspot. So that's where the issue pops up, and that could slowly expand to or extend to the other cells. Ultimately, battery pack will fail or battery pack will get into flame. So in the active cell balancing, what you normally do is, so this is again, uniform. Now you look at, okay, let me see. So in the active cell balancing, the energy from the better cells are redistributed to the poor performing cells or weaker cells. Or in other words, the energy is distributed, excess energy is distributed throughout the system. But then, you need to individually monitor the cell. You need to relate to how the performance was until then and how the performance is going to be after this cell balancing. These are all done in the little more advanced battery management system. But in the AI enabled, it's going to be much involved cell balancing. Okay. So if you look at here, so there are charge control, discharge control, state of health, and state of charge monitor, and obviously, better way to inform the user. The charge control, it's not just based on the energy. It's also doing based on the duration, smaller t, voltage maximum, cell voltage base, change in voltage, because as we charge the battery voltage is going to be a little more stable until the battery becomes fully charged. Towards the end, maybe after 98%, voltage profile will jump to the maximum value quickly. So change, this delta V, so change in voltage value is also monitored. At the same time, delta T, capital T, that's the temperature. Because as the battery gets fully charged, the input energy is not going to be accepted for changing the material from discharged to charged state. So temperature is also going to rise. So you monitor the temperature increase. So change in temperature rate is also being monitored to control the current. So towards the end, it may stop the charging or switch to lower charging current. That's more smarter battery management systems role. And in the discharge control, so it is going to obviously monitor the state of, discharge rate, that's a current. So current will also be limited. When the battery voltage becomes lower and lower with the usage of the battery in the vehicle, current capability in most of the batteries will become poor as the battery gets discharged. So the smarter tools will say, it keeps learning from the battery system. It keeps learning from the operating conditions. So it gets the data right from beginning, and it also learns through the process. Because the system or the smarter or more smarter AI-based one is obviously going to develop a predictive thermal management model. It will expect if the battery is at, say, for example, 30% state of charge, you can still go down until you hit 10% state of charge. But the way it manages the thermal characteristics at 90% state of charge is completely different from 20% state of charge, because it's learning, it's understanding what is going on, and it's going to develop everything is so fast, everything happens through the edge AI, because you cannot have data stored in cloud, because you don't want to have any kind of latency. You want to do everything instantaneously. The battery management system is very local, so that's why it's going to be edge AI based tools. So everything is internal, everything is quicker, with a minimum time lag, right? And also the state of charge and state of health indicators like gas gauges, it's also going to factor in, how the user is using the vehicle or the battery load for any other applications, what is the typical speed, what is the time duration by which, all the duty cycles, operating temperature, even self-discharge if the vehicle is, parked for some time, and also charge rate. All those parameters are factored in to develop a model, and everything is, again, the model is used to make a predictions, and that prediction is going to be very, very precise in the AI-based tool. When the prediction is going to be very precise, whatever happens in terms of thermal management is obviously going to be extremely precise and accurate for the users. And that will improve, because when you thermally manage it perfectly, you get the optimum energy output or range when you drive, and obviously the cycle life or calendar life, whichever is going to be considered. So in other words, you want to minimize cell to cell variations, and also minimize the degradation overall, absolute degradation, and also cell to cell variation should also be kept as minimum as possible, because it will never be zero. So this just again, just a picture to show you that a typical AI-driven BMS system with edge AI tools and sophisticated sensor-based BMS will predict the state of charge, state of health, and also remaining useful life. Most of the times, you want to have the BMS, which is going to be like not reactive, but it has to be proactive. It should be in a position to have a predictive capability and also prescriptive capability. That's exactly we want. And that's not easy unless we collect a lot of data. So the big data analytics is part of this edge AI based or AI enabled battery management system for the EV. And this is certainly going to happen in the next decade or so. So this is a typical difference, right? So if you look at the traditional or a relatively smarter battery management system, everything is so static, so constant voltage and current, fixed threshold, and limited adaptability. But then the AI enabled, it develops a predictive models, and it also has an adaptive control. So in other words, it's going to be more agnostic. It's not going to be dependent on any kind of very specific use case scenario. And suddenly life is going to be extended. You put the battery in a situation that is perfect for the operation, mainly for performance. These three are very key, right? Performance, safety, and life. And when you talk about the safety and the life, it is also telling you the reliability. So you can just go in, all those kind of range anxiety or charging anxiety, it's all gone. Even now with the smarter AI, not AI based, but smarter battery management system, these are all kind of gone. But with the AI driven BMS, all those issues are going to be, forgotten. So, certainly, you will be analyzing the battery usage patterns and obviously the environmental conditions. That environmental conditions are, road, posted speed, and also whether the driver is kind of, driving in the city or highway or aggressive or normal drive, or whether it is based on, really a crowded highway, or maybe, these AI tools are obviously going to also sense the traffic speed. It brings in what you expect, right? So whatever you want to do, the AI-based BMS is going to monitor and do it. So suddenly it's going to learn. It's going to learn. Like, I know most of you probably use the Nest thermal system or temperature control system at home. So the system learns from the use case scenario, and suddenly that's exactly is going to happen, or already happening in the experimental level in most of the big EV companies. So this is how the workflow, suppose if you want to develop AI-based BMS system, right? So suddenly, if you look at the number one, so that's a gap. In other words, we do not have the optimal design for the battery thermal management system, specifically for the EV lithium-ion battery system. So for that, what is important is the data collection. So, what kind of data are needed? Basically, you need to study, you need to collect the data, you need to understand the data, how the battery performs, develop a model, and use the Pearson analysis. So that's a typical tool for regression analysis or correlation analysis. So you predict from various parts and various parameters as to how they influence the major output. That's again performance, safety, and the cycle life. And we would also be using the Pareto charts or Pareto points because you want to know which one is the most critical from the trivial many, right? So once you have data, then you develop a ML model, and then you optimize via AI algorithm. Most of the times people say you may use the MOSA or multi-objective swarm intelligence-based AI algorithm, and then you connect with the real world scenario because whatever you do, it has to work in the real life scenario, and then you make the decision. So this is a very typical flow for the AI enabled BMS design and development. This is a very simple kind of a flow, and also as to what happens in the AI ML based BMS. So first step is always to track voltages with the sophisticated sensors. So voltage, temperature, and current. So current measurement has to be very accurate, and obviously if we can if you know all the battery characteristics right from the beginning, we can key in all those parameters. But this is during the operation. And once you measure these values accurately, then you can control the overcharging or overheating, because that's what happens towards the end of charging. And then it tells you, when you control the overcharging, what is the charging level, whether it is a 95% state of charge or 99% state of charge. The goal is always to extend this useful energy. You want to go beyond 5% at the bottom and also go above 95% or 98% on the upper side. So you want to maximize the usage, because for example, if you have a 100 kilowatt hour battery, that's a rated capacity, and you want to use all the or closer to 100% capacity, but in a very safe manner, and also without allowing the batteries to fade or age quickly, right? So alerts for any battery issue. So you need to understand, you need to have the tools which would expect that something is going to happen, right? So again, as I said, like a predictive level of predictive and prescriptive level of performance for these AI tools manages battery temperature. So this battery temperature, the battery, keeping the battery temperature in the sweet spot also is very energy expensive or energy intensive. Lower temperature, ambient temperature, you need to heat. Higher ambient temperature, or when you drive the vehicle at high speed, you also need to control the temperature and keep it below 40 degrees or closer to 35 degrees Celsius for keeping the battery in a safe operating conditions, and ensuring uniform charge. So that's a uniformity, right? So cell balancing, you have to keep that really balanced, and that has to be done almost on a regular basis, not just during the charging. So it has to be much more than active cell balancing. And obviously the battery management system has to interface with the vehicle system and optimize power management. Power and energy management is very critical, right? So when you drive faster or when you charge faster, both are same for power management for optimum efficiency. But at the same time, I said typical is like a 4 miles per kilowatt hour. So you need to have a very good control on energy usage, mainly for useful purpose. So all this auxiliary power management for thermal management, it's considered waste if you are looking at the main EV battery for range. You want to minimize the energy usage for the auxiliary applications. So before we jump into the, I have a few slides on the Tesla vehicle. So this is exactly is happening right now in the EV industry. You may say this is almost like a Russian doll. So you start with the electrodes, anode, cathode, and current collectors and all those things, and assemble them into cell. Then you have multiple cells, and you make modules, and multiple modules get into pack, and pack goes into the vehicle, right? So it's changing. You want to avoid one step. You want to have cells, and you want to directly assemble the cells into the pack. So this is cells to modules to pack. So here it is a C to P. So in other words, you cut this operation or you limit this operation. In other words, you may be able to pack more cells in the same volume without making another step as making modules. But I think this is the ultimate. This will certainly happen in the next 2 decades. Cell to pack or cell to chassis, cells to vehicle itself. You have a kind of a particular location in the vehicle. You assemble the cells directly into the chassis. You are now eliminating the module and eliminating the pack. So for this, you cannot use a simple battery management system. That is exactly, we need really smarter AI-based battery management system, because, there's no additional protection, right? So here, if something happens in one of the cells, thermally, you have, primary, like a control, you have, casing, you have enclosure, right? All these pack will have like a IP67 or IP69 rated packaging. Now you come back to the module, that's additional. So you have a primary package, a secondary package, a tertiary package. Now you avoid everything and assemble the cells directly to chassis, because that is going to maximize your utilization of the space and weight or volume in the vehicle. Or in other words, you can pack more energy in the same vehicle so that you can have longer range if you use the same battery size. So that is what you need, AI-based battery management system, and that's exactly happening now. So now let's go into the vehicle as the one we have in the lab. So this is a 100% interactive demonstrative EV. It's a brand new Tesla Model 3 vehicle. It is still, it's still connected with the Tesla system. When we turn on the vehicle, even though it's in the lab, it's not hacked into the system. So when we turn on this vehicle, it connects to Tesla. They know what we do. So, but again, this is a training vehicle, and most of the places you have cutaway sections that you can look at the component, you can understand what happens for any kind of like a troubleshooting, for electrical, thermal, and also operational. You can do everything. You can even you can control the sensors. I think if you get into the maintenance mode, you can even calibrate those sensors. All the camera and sensors can be calibrated. Only thing is that it does not have the 400 volts battery system. That is removed for improving the safety for training with all the participants. So this is actually a picture in the vehicle. So you see all the orange colored cables for all the high voltage systems and low voltage system based cables are all in black. And it also actually, I'll show you, it also has LEDs for electrical and thermal operations, or flow and everything. 100% of the EV operation can be understood by spending few days around the vehicle, because it's always going to have all the theoretical aspects required for the vehicles, including battery characteristics, all the electric powertrain, because the training modules combine both theory or operating principles theoretically along with the lab experiments. The best way to learn about any system. And this is a real 100% hands-on training system. And the system has about 5 modules. So typically I think each module takes about a half a day. So 2.5 to 3 days are more than sufficient for learning about this electric vehicle. But obviously you can simulate many different operating conditions. Let me show you here. This is part of the training system. So you can actually accelerate, you can fix the speed at a particular value preset, and understand how the battery voltage changes. You can understand how the temperature changes. So everything is kind of simulated, but in the same vehicle, right? So you can understand how the battery voltage changes, what is the current when the speed is set to a particular value. You can do charging. You can actually select, because there's still the charging port. You cannot connect a charging gun, but at the same time you can set everything here. So whether you do the level 1 charge, level 2 charge, or level 3 DC fast charging, you can understand extreme fast charge. So as per Department of Energy, as long as you can charge say close to almost 30 miles per minute, that is extreme fast charge. But you understand what happens with the battery temperature. All those characteristics about the battery thermal characteristics could be understood. And you can basically drive the vehicle. You can sit in the driver's seat. You can understand what's happening when you do different operating conditions, like cold weather, normal, hot weather. These values can be set to a particular value, and then understand what happens to the battery, even range per charge. And also you can actually simulate what happens to the speed by setting the vehicle to, or the battery to, any particular state of charge, right? And you can also set the in-cabin temperature also to a particular value, whether you want to heat the cabin, assuming that the ambient temperature is lower, or cool the cabin temperature to a particular value, assuming that it is Arizona summer weather, right? So many things, or I will say every aspect in the electric vehicle can be clearly learned through this system. And most of the times, the purpose is that if somebody spends a few days and understand all the operation, understand all the physics principle behind, and understand high voltage, right? So we can also measure the insulation voltage values for the high voltage system, because that's what is important. This is one of the pictures that we took from the same system. So all the location for the battery management. This is obviously it's not a AI enabled BMS, but that the system performance or reliability can be enhanced to the next level with the AI enabled. Like I said, the system at the operational level has the details on electric motor or power electronics controller, DC-DC converter or inverter, all the cooling system and the heating system with clearly identified components. And also it comes with, more details as what the operation is, what the purpose is, and then, how they perform, what is the efficiency, and entire, I will say, energy to wheel, or whatever you want to call. So like, well to wheel, this will be energy to wheel or range. So thermal, towards the end, I think thermal management and safety, this does have, coolant. This is actually the LED. This is not lit right now, but you can monitor the voltage when you turn on the thermal management system, because in the vehicle, the thermal management system consume about, most of the vehicles have like a 5+ kilowatt power. So in other words, if you have a 100 kilowatt hour battery, if you operate the vehicle for 3 hours, whether it's cold weather or hot weather, with a 5 kilowatt power, it's almost like 15%. 15% of the total energy from the battery is gone for auxiliary applications. So you cannot afford to maybe spend this energy for other uses than the driving purposes. So that's the whole idea. So, like I said, we can also, this is how the battery modules are integrated in a real vehicle, because as I said, this training vehicle does not have the battery, but you can simulate and you can understand the cell voltage. You can, monitor cell voltage as how they change. You can also, set one or two cells to lower voltage to learn about the troubleshooting in the vehicle itself. I think I'll stop here.
So much for Dr. Kalam. Go ahead, Benny.
Oh, yes. Well, thank you. That was wonderful. I know we have some questions in the Q&A. While we give Dr. Kanan a minute to review those Q&A questions, I did want to just ask, do we have a poll lined up for this, Nikki, or are we going to put this in the chat?
We're going to launch the poll.
Okay, so we're going to launch a poll that will appear on your screen, and if you don't mind, I think we're curious about, after today's session, which area of EV systems do you feel is most important for technicians to master? And this just helps us understand on a holistic view. If you have thoughts or ideas around this, would just love if you took your moment to fill in this poll. And we'll give this just a second if you can make your selections, and then we'll move into our Q&A time. I did notice a question that popped up in the chat during the presentation. This webinar is recorded and will be added onto our website as well as onto our YouTube channel. So Nick put the information for those links in the chat. We also send out follow-up emails, so you'll receive that as well. How are we doing, Nikki? Should we close the poll up?
I still see people are trying to answer.
Okay.
Yeah.
We'll give you all just
We give it a
another
little bit.
moment.
Yeah.
And also take a minute if you do have questions that came up as you're waiting for others to finish the poll. Please do add any of your questions to the Q&A. I know that was a lot of content we talked about. Some great questions in here.
I'm going to
Okay, so
close
if the poll is closed, so I see one question which says, are the data available as a open source? Yes, there are data available in open source, but unfortunately, those data are not relatively newer. So if you want to get, I think that we looked at some of them actually yesterday, and the student said she could actually download data from a DOE website, which was probably like a 2017, or the previous one was like a 2008. But as I mentioned, these, especially battery technology is, changing day by day. And like I said, the batteries manufactured today will work much longer than 15 years in the typical operating EV, right? So to some extent, the answer is yes, you can still get to some data, which is probably not proprietary, but there are many recent literature, through journal publications that, around the world, they work on lab simulated cycling at various operating temperature and also various charge discharge rates. Those data could be used for understanding, or to even make a model to predict the state of health, because that's always one of the toughest one in the battery industry. So it's almost like a human being, right? A doctor can never predict the life of the person accurately. To some extent, yes, but not so accurately. So battery life prediction is a little tougher, and that's where the AI tools are going to be used effectively. So Yeah, battery range, I think it's going to have a huge influence. That's because you will be using the energy in an intelligent manner. So in other words, battery's energy is not going to be underutilized or overutilized. So because the purpose of this high voltage battery system is mainly for driving. You want to minimize the auxiliary energy use. So it's basically how effectively you manage electron flow. And that is done perfectly by this AI-based BMS. With time, I think it's going to become more smarter, more sophisticated. But again, a typical battery management system, probably like, whatever we had 20 plus years ago in a lead acid battery EV, you would have seen like a 4 bars. One would say, or maybe 10 bars. One would say, oh, you have 10% energy left or 20% energy left. But now you see in terms of number of miles. But even though you get a number of remaining miles before you charge, is not near accurate. But the accurate prediction is going to be the outcome in the AI-based BMS. But overall, the range is, with the minimum usage for auxiliary applications, the range is going to be extended. And you operate in the optimum or the best operational conditions, that cycle life is also going to be extended. So basically, you can precisely estimate the battery's state of charge and state of health, because these are not same if you measure for the battery which are relatively newer. The newer battery and the older battery, the way they change the state of charge under identical operating conditions are completely different. So the system should know how the battery degrades. Accordingly, all this predictive algorithm will change based on the life of the battery. In other words, the algorithm used for measuring the state of charge and state of health is not same today or after 1 year for the same battery system. It will be different. The system has to understand how the battery characteristics change with time. That's how it's going to be more smarter. And safety, right? So certainly it is going to, the system is going to manage the battery in a particular or optimal temperature range, because that's the cornerstone for the battery safety. And you cannot overcool, because you are going to also pull power from the same battery. You have to have a minimum, but you have to also keep the battery temperature as close as to the best temperature scenario. And one of the main thing is the fault detection. The system would expect, because it monitors the performance, they'll say, oh, something is going to happen, and you trigger all these preventive kind of maintenance activities if required, whether the user can do in a particular time, or it is also going to be done at the service center. So basically you expect what is going to happen next week, so the system alerts you to take it to the service. And the efficiency is one of the parameters, right? So again, all these are kind of cycles. So you have a better managed system is always going to have a better efficient system. And so basically performance, safety, and reliability. Okay, so one of the questions is what is the main difference? Main difference is a typical BMS is reactive. Whatever happens, it just tells you what is to be done. Whereas AI-based BMS is proactive. and it would respond to any kind of a dynamic situation, and that's actually happens in the regular EV. So life is going to be extended, but I would say, people always talk about smarter, more smarter AI-based BMS. You may say your SOC predictive accuracy is going to be well within 1% of actual. Maybe the state of health prediction is going to be well within maybe 3%. The goal is always to have much, much better predictive characteristics from the AI-based BMS tool.
Dr. Kanan, I think we're about at time. Was there one more you wanted to answer before we wrap up today?
Okay, any question? I don't think there is any, but I would end by saying that AI-based BMS would give you, I would say, extended range, or enhanced performance, enhanced safety, and also extended battery life.
Excellent. Well, thank you. Very much appreciate all of you joining today. I know I've learned a lot throughout this presentation, and hope you felt the same. I wanted to, I think I missed one slide here. There we go. I know some of you might have heard about this event through Dr. Kanan's course. If you have not, we do have a publicly available course about battery technologies. I invite you to check it out if you're not currently familiar with this. It's live on Coursera, so you're able to connect through that platform. Additionally, if you're interested in learning more about this topic, either individually or around group training on similar topics, feel free to reach out to us. Happy to talk more. We'll share these slides, and our recording of the presentation will also be on the website and YouTube as mentioned. And lastly, most importantly, just want to thank all of you for your time. Thank you, Dr. Kanan, for joining us today and sharing your work. Please consider registering for our next session, and we look forward to connecting with you again soon. You can stay in touch with us on LinkedIn. This has a quick QR code you can scan, and we do have an engineering professional development page where we post a lot about these types of opportunities. So thanks again. Appreciate you joining.
Thank you very much.
Thank you.
Bye-bye.